Okay, so welcome everyone to, this is the last seminar before Easter, so we have a break next week. This is the last one before the break. We're very happy to have Jeff Calder. Jeff is an assistant professor at the University of Minnesota. And before that, he was at in Berkeley, and before that, he did his PhD in Michigan. We're very happy to have him today. He's going to be talking about random walks and PDEs in graph-based learning. So thanks, Jeff.
Okay, yeah, thanks, Matt, for the kind introduction and for the invitation to speak. So I'm going to talk about two problems in this sort of intersection of random walks and PDEs and graph-based learning. This is joint work with several different people, including my PhD student, Brendan Cook. So, the object in this talk will be a graph. So we have vertices X and edge weights W. The edge weights are always non-negative, and the graph will be symmetric in this talk. And the idea is that the weights W, X, Y are large when X and Y are similar, and they're small or they're zero when the data points are not similar. Here's an example of a k-nearest neighbor graph built on a toy data set that has two distinct clusters with a small bottleneck between them. And so what you can see here sort of are that, if you wanted to identify one cluster versus the other, the kinds of things that might be useful are things like random walks or diffusion processes on graphs, because if you sort of take a random walk starting over here, you're likely to end up exploring much of the brown nodes before you cross this small bottleneck to find the other section. So sort of clusters that trap random walkers for a long time are sort of good candidates for meaningful clusters in your data set, and these are the kinds of things that we'll see throughout the talk. And so graph-based learning tasks include things like clustering, like I was saying, so grouping similar data points together, or semi-supervised learning, which is propagating labels on a graph. So in this context, you might give a couple of the blue points and a couple of the red points labels as blue or red, and then say label the rest of the points in this graph. And then there are other applications like dimension reduction and embeddings and things like this. So for a concrete example, we can look at the MNIST data set. This is 70,000 images of the handwritten digits from 0 to 9. Each data point is this 28 by 28 pixel image of one of these digits. And you can treat this in sort of a very naive way. There are better ways to do this, but you can treat this as sort of vector in a high dimensional space by just flattening the image. Okay? And you could construct weights in your graph as geometric weights, where you take the weight between X and Y to be some kernel eta applied to the distance between X and Y scaled by a bandwidth epsilon. In practice, the same epsilon over the whole graph is not so great because you have dense and sparse regions. And so it's more common to use a scaling bandwidth epsilon, which sort of varies throughout the graph and is adaptive to how dense the graph is locally. And so one way to do this is with the k-nearest neighbor graph, where you tune the bandwidth to be like the distance to the kth nearest neighbor, let's say. So if you wanted to cluster MNIST, this would be just separating the different digits, zeros, ones, and twos, and so on, into their own groups. Here's a visualization in 2 dimensions of a clustering of MNIST. You can see that there are some pairs like the zeros and ones that are pretty easy to separate, whereas the 4s and 9s are a lot more difficult. So this talk will be mostly on graph-based semi-supervised learning. So we have a graph, and on the graph, we have some small subset of labeled nodes, gamma. And on those labeled nodes, we have labels, which is this labeling function G. And our labels are vectors in RK. And what you should be thinking is that in a classification problem, the ith class is represented by the one hot vector E sub I, where you put a 1 in the ith coordinate and the rest are all zeros. Okay? Although for most of the things we talk about in the talk, this function G could be anything, and you could have any vector valued function that you like. And so the task in graph-based semi-supervised learning is to extend these labels you're given on maybe a very small subset of the graph to the rest of the graph in some meaningful way. The reason it's called semi-supervised is that the goal is to use both the labeled data, which is the set gamma and the labels G, and the unlabeled data, which is the rest of the graph, in order to get good performance using far fewer labels than you would in fully supervised learning, which would only use the labeled data. Applications of semi-supervised learning show up in lots of problems where it's costly to obtain labels because a human has to look at data to assign a label, but we have an abundant amount of unlabeled data that we can use to improve learning outcomes. So this includes things like speech recognition, image, video, website classification, and some problems from mathematical biology, among many other applications. So why is it useful first to look at semi-supervised learning? Like how can we use the unlabeled data to inform a classifier? And so this is clear when you have very few examples from each class. So say I just have one example from each class, from the red class and the blue class. If this is all I'm given and I'm told to train a fully supervised classifier on this, all I can kind of do is draw a line between the two classes that's equidistant from these 2 points and say my rule for classifying new data points is that if they fall on the left side, they're red. If they fall on the right side, they're blue. And then, so someone gives you a bunch of points, these black points, and says, these are the points I want you to classify with your classifier you just trained. And these are the only points I want you to classify. And so your classifier is going to say these are red, these are blue. But the point is that, if you had access to the black points beforehand, before you trained your classifier, you could actually use those to inform your decision boundary, and you might move it over here to the space between the two clusters. So being aware of the unlabeled data can be very useful in classification. So one of the oldest methods for involving the unlabeled data in the classification in the graph-based setting is to use Laplacian regularization. So here you solve the Laplace equation. So you do the harmonic extension of the labeled data. Okay, so this is just the unnormalized combinatorial graph Laplacian. Keep in mind, this is a vector valued function u. And so really this equation has like k separate equations, one for each component of u, and these labels are the one hot vectors for each label. Once you solve the equation, you decide on the class membership for each node by looking at the component of this vector valued function that's largest at each node. Okay, so you can think of the function u of x as like some kind of vector of probabilities that x belongs to each class, although they don't actually sum to 1 in this case. So the original work is by Zhu, Graham, and Lafferty in 2003, and this is one of these very widely cited papers that's had a huge influence on the field since then. And there's, here I reference a few papers, but there are tons of papers in graph-based learning which use ideas that came from this seminal work. So a couple of comments about Laplacian learning. So if you take the condition of being graph harmonic and rearrange things a little bit, what you get is the mean value property on the graph. The graph harmonic function is equal to the weighted average of its neighbors. Okay? And you might also see in the literature something called label propagation, which propagates labels on a graph by replacing u of x by the weighted average of its neighbors until convergence, setting the labels at each step. And of course, when this converges, you get a graph harmonic function that's the same as Laplacian learning, but this connection is not always made in the literature. So we're talking about Laplace learning and label propagation here. Of course, if you're a numerical analyst or a PDE person, this kind of iteration for solving Laplace's equation is called the Jacobi method. And it's like the first thing that you learn about when you take a course in undergraduate PDEs. And it's one of the slowest iterations you can use to solve an equation like this, unless you combine it with a multi-grid approach or something. So, there are much faster ways that you can solve the Laplace equation, like the conjugate gradient method or something. So it's also important to point out there are variational interpretations to Laplacian learning. So here it's you write down the graph Dirichlet energy, so the sum over all edges on the graph of the squared difference of the labels at those two nodes multiplied by the weights. So you're minimizing the Dirichlet energy. Think of it in the continuum as the integral of the gradient squared, the function u. So you're trying to find the smoothest function that interpolates the given labels. There are tons of variations on this where you replace the hard label constraints by soft label constraints. And you have a penalty parameter lambda, and you choose your sort of favorite loss function, if it's L2 or it could be cross entropy loss or something like this. There are lots of different variations like this have been proposed. You can also change how you normalize the graph Laplacian, so you can change this Dirichlet energy a little bit. so it's been noticed like in the last 10 years or so that there's a certain degeneracy in Laplace learning at very low label rates. What happens is say you just take these two labels like I had before in a previous slide, but you take a really large graph. So I take a box and I take 100,000 points in the box. I build a graph over this by connecting points nearby. And then I just stick two labeled points at the red and the green point with label values 0 and 1, and I solve the Laplace learning equation on the box. The image on the right side is what you get, and what I've done is I've just interpolated the function from the graph to a grid so I can plot it as a surface to sort of show you. You have it's constant almost everywhere, and actually these spikes are a bit wider than they are in reality because there's some smoothing from the interpolation to the grid. So you have this thing which is basically constant and it has these sharp spikes at the labels. So the solution wants to be constant, but you're forcing it to attain the label values. And so this was pointed out by Nadler in 2009. It's not something that's just, academic and doesn't show up in practice. It really gives poor results when you apply it to classification at low label rates. So here's an example on MNIST. I'll tell you later how the graph was built. If you look at, MNIST has 70,000 data points. And so one label per class is pretty close to the example in the previous slide where it's like 100,000 points in like one label. And so,
Jeff,
sorry.
we have a question in the chat.
Sure, of course.
So I'll interrupt you if that's okay. So this is from Mark Pelletier. He said, is this the same phenomenon as that points in R2 have 0 Laplacian capacity?
Yes, it's exactly the same thing. Yeah.
Okay,
So I didn't really expect any PDE people to be at this talk, but maybe that's
sorry.
I don't usually give that interpretation. Yes.
Thanks.
Yeah. So there are like many different ways to think about the fact that you have these spikes showing up in this Laplacian learning. And it's exactly the fact that like in Sobolev space theory, you cannot define the trace of functions at points. The capacity of a point is 0. You can't set boundary conditions at isolated points when you're solving elliptic PDEs and so on. So there are countless ways you can sort of think about this. I'll show you the random walk interpretation, which is actually very useful to think about later on. So what we're seeing here is that, at very, very low label rates, like 1 to 4 labels, the performance is sort of catastrophically bad, although it improves a bit. And, why do I say catastrophically bad? Well, it's much worse than like a nearest neighbor classifier, which should not be the case. And you can do clustering you can do clustering with no label information on MNIST and get like 97% accuracy. So it's a very well clustered data set. Getting 16%, which is very close to random guessing, is catastrophic. Okay? And it's not that it's a bad algorithm. If you take 160 labels per class, which is about the smallest where you get really good results, it's 97% accuracy. So it's a good algorithm when you have a moderate amount of labeled data. It's catastrophically bad when you have very few labels. So this has been, a stream of work has been coming out on this like in the last 10 years. What can you do to fix this? So you can look at higher order regularization where you take a power of the graph Laplacian. You can look at P-Laplacian regularization where you take the Dirichlet energy, take it to the power P instead. Both of these have motivations from Sobolev space theory where you say here, the first one I'm going into WK2 for a large value of K. So I'm looking at higher derivatives and I have an embedding into a holder space. I have continuity at the labels and so everything's nice. The same thing with the P-Laplacian. If you're in W1P for P bigger than D, you have continuity and you have you can't have these spikes forming. You can think about reweighting the graph. So the reweighted graph Laplacians, which started in this paper by Shio, Shi, and Zhu, and then we followed up with a follow-up paper doing this a bit more rigorously. Here you take the graph and you amplify the edge weights that are attached to labeled nodes by very large factors. And this sort of discourages spikes from forming. In the first paper, they only did this at the nearest neighbors of labels, and this still becomes ill-posed. You have these fatter spikes showing up. And then we showed that if you sort of reweight in a non-local neighborhood in a very singular way, you can actually define the trace of functions at points, and you can recover the boundary conditions at isolated points. And then there's a completely different idea called the centered kernel method, which is based on high dimensional random matrix theory. So we have a lot of sort of new ideas for avoiding these spikes. We're trying to overly regularize the problem to get rid of these spikes. But I think until the work I'm going to talk about today, there's not been a really solid understanding of, you know, where these spikes are coming from and why they're a problem for classification. And so we'll dive more into that in this talk. So this first part will be on, you know, how large are these spikes? You know, why are they occurring? Can we control them with high enough label rates? And the second part will be about, you know, what do you do in the very low label rate regime when you do have these spikes forming. Here's a higher resolution version of the spikes that I'm talking about. So this is, I'm going to be sampling a function cosine of x1. And I, again, have like a graph on a box with 100,000 random variables. I'm taking 10, 100, 1,000 labels, and you can see how, you know, at 10 labels, you have these very sharp spikes. And here it's actually a very high resolution plot of the function on the graph, exactly. And you see that the spikes are like at a single node in the graph, and then you drop down immediately at the neighbors, right, to this sort of second order behavior. Once you have 100 labels or 1,000 labels, you can see cosine better, and maybe at 1,000 labels, the spikes are kind of like negligible. So the first question is, how many labels do you need to ensure that the spikes are controlled and they don't form? Why is 1,000 okay, but 10 is not? Right? And then the second is, you know, okay, so say what I really want is to classify correctly in the end. Why is it the case that Laplace learning performs poorly at these low label rates? Is it because the spikes are too localized? They don't propagate information globally? These questions had not been answered beforehand. It sort of turns out that the spikes are not really the problem, we'll find in the end. And if you deal with them correctly, you can get a method for propagating labels in a stable and informative way. And that will be the last part of the talk. Right, let me, I think I'm going to skip through a little bit of that slide. Sorry, I'm gonna skip over one of my slides and just jump right to the random geometric graph. So the model for the graph that we look at is a random geometric graph where I have the vertices are IID random variables on a domain in RD, and then I have a positive with some positive density function rho, and the weights in the graph are the geometric weights that I showed you earlier on. So you choose some positive smooth kernel that has compact support, and it could be a Gaussian oftentimes, but really it doesn't matter so much for the theory. And then, okay, so in this setting, the graph Laplacian, if you plug in the weights for the graph Laplacian, you have this eta of x minus y over epsilon. So if you take the large data limit as n goes to infinity and the sparse graph limit, it's well known that this operator L is consistent if you apply it to a smooth test function. It's consistent with a weighted Laplacian. So it's minus rho inverse divergence rho squared grad u. So it's weighted by the density rho. So in particular, you can actually prove quantitative convergence rates with high probability, which go back to papers by Hein in 2007 or so and have been used a lot in the literature since. So you get order epsilon convergence rates between the rescaled Laplacian and the weighted Laplacian here with high probability. And so what one should be thinking sort of is that this density rho in here, it's controlling the speed of the diffusion. So you have faster diffusion in dense regions of the graph, and you have slower diffusion in sparse regions, which is sort of exactly what you want for propagating labels. You want them to propagate quickly in clusters, and then to propagate slowly between clusters. Right? You can think of this sort of from image processing, kind of like as an edge detector, which allows you to have a sharp change in U between clusters, very much like, you know, a Pronomalk equation or like total variation regularization in image processing, if you're familiar with these kinds of things. Except here it's a linear equation. Rho comes from the data, and it's not dependent on the on grad u. Okay, so in order to understand how many labels we need to control the spikes and to get a well-posed Laplacian learning algorithm, we need to take a model for our training data. And so here I'm taking my domain omega, where I have all my vertices sampled for the graph, and we'll fix some subdomain omega tilde. And within omega tilde, I'm going to randomly choose a fraction of the points to be labeled. And so for every point inside omega tilde, it's going to be assigned to the training set with probability beta, independent of all the other points. And so beta fraction of the points will be labeled. And then gamma n is the training data, the red points here. And then we solve the Laplacian learning problem with the Dirichlet boundary conditions, the labels at the red points, and we assume the label function is Lipschitz in this result. So what you expect in the limit is that, if the red points are dense enough in the limit, they fill out the domain fast enough, that the limiting function as n goes to infinity is going to satisfy the Dirichlet condition on omega tilde, and it will satisfy the PDE with a weighted Laplacian on the rest of the domain where I have no labeled points, and then a natural variational boundary condition on the boundary of omega. And this is what we get. So this is the PDE with a weighted Laplacian, the Dirichlet condition, the normal derivative. That's not so surprising. The interesting thing in the result is what is the smallest label rate for which you get this well-posed continuum limit compared to getting the spikes forming and things are converging to a constant. So the label rate threshold is beta is equal to epsilon squared. So epsilon is the length scale for the graph. So as long as the fraction of labeled data is much larger than epsilon squared, then the discrete problems converge in the continuum to the solution of this PDE, so the spikes go away. And they go away with this rate epsilon over square root of beta. Okay. And so this is a finite sample size sort of high probability statement here. Let's see. So the point to make is that this label rate is still allowed to vanish as n goes to infinity. You can send epsilon to 0. And this label rate can still go to 0. It just can't go to 0 that quickly. It has to be bigger than epsilon squared. Let me tell you about the proof very, very briefly. So the proof uses random walks. So this is a way to avoid having to explicitly deal with the spikes in these solutions, which are very singular and hard to deal with. So you take a random walk on the random graph. And so the random walk is the usual one. We're going from x to y. The probability is the weight x to y over the sum of all the outgoing weights. So this is the degree here. And you define the stopping time as the first time the random walk hits a labeled node. And then you have the classical formula for the solution of the Laplace equation in terms of the random walk is that the value un of x is the expectation of the label that you hit first with this process. Okay, and it follows just from the fact that this un of xk is a martingale. Okay, so this is just Dub's optional stopping theorem. Now, once you have this interpretation of the Laplace equation, you just take the difference with the label function g, take absolute values, and then on the right-hand side, what you're doing is you're going to use the Lipschitz constant of g, pull it out, and what you're trying to bound now is the expectation of how far the random walk moves before it stops. And so this is the whole thing is like, how far does your random walk move before it stops? If it moves too far, you're averaging on too large of a scale, and things are going to become degenerate. If it stops quickly, you're going to be averaging on local scales, and you'll sort of recover the label function. And so how do you bound the stopping time, or the distance that you travel until you stop? Well, there's a condition in the theorem that comes sort of from the probability. So to make this probability not vacuous, to make it close to 1, epsilon has to be large enough that every point sort of has a beta fraction of its neighbors are labeled. So you have labeled neighbors of every point in the graph. So it's like every step of the walk, you have roughly probability beta of jumping to a labeled point and stopping. So the number of steps until you stop is like 1 over beta, essentially. It's just a geometric random variable. And then you ask how far does the walk move in 1 over beta steps. So for a simple random walk going by epsilon each time, it would go square root k times epsilon in k steps. And the same thing you can prove holds for random walks on random geometric graphs. And so if you plug in the 1 over beta into k here, this gives you the epsilon over root beta rate. That's how far the random walk moves with very high probability before stopping. Okay, so it's a very sort of nice soft proof. It doesn't require a lot of hard analysis, but gives you the right kind of scaling. So we have the negative version of this result too, which says that if I take a sequence of problems with label rates going to 0 faster than epsilon squared, then everything is sort of degenerate, and if there's a convergence subsequence, it converges to a constant, and so you have these spikes forming. So this is a very sharp label rate restriction. You can't violate this and control these spikes. So this tells you, okay, if you want to use Laplacian learning, you should use it in a condition where the label rate is at least bigger than epsilon squared, and you should be somewhat guaranteed to get reasonable results. This does hold out pretty well in practice. So we tested this on MNIST, and we compared the test error to a number of labels in each class. And okay, it's, it fits roughly to this 1 over root beta shape. Test error is not the same as the theorem I wrote earlier, but it can be used as sort of a surrogate for this. It's even though it's sort of on average beta to the -1/2, if you do a log plot, it's not exactly straight, so there are some different fluctuations here, but it sort of explains kind of what we see in practice here. There's a second model we looked at in our paper, which I won't talk about too much here, where you sample the labeled points only in a tube around the boundary, and your continuum problem is just the weighted Laplacian is 0 with Dirichlet boundary conditions here. And you have the same kind of label rate restriction showing up. So, okay, so now that we know, what's the sort of exact label rate at which I can use Laplacian learning, and we should look at the problem of what if I want to do learning on graphs at much lower label rates, where I'm going to see these spikes forming. What should I do? Okay, so it's useful to look at the random walk perspective here. So just like we saw in the previous proof, I take the solution of the Laplace learning equation and I write it in terms of the random walk interpretation, so the expectation of the first label that I hit in this process. You can see why it's a reasonable thing if you have enough labeled points that you hit something fairly quickly. If I start the random walker in the Brown region, if it stops, in a short time, it's likely to have remained in that same cluster and hit a correct label from that cluster. It's less likely to have traveled across the bridge between the two clusters and hit something in the other side. But we can see why this becomes a problem at very, very low label rates. If I take, if the walker takes too long to find a labeled point, it can easily leave the cluster it started and explore other parts of the graph, and eventually sort of pass the mixing time for the random walker, so that the node that it ends up hitting is sort of largely independent of where it started. And this is exactly what's happening on, let's say, the MNIST experiment from earlier. So we ran some simple experiments where I just, in place of solving the Laplace equation, we used the random walk interpretation. So we released random walkers from one of the MNIST images and counted how many steps it took until it hit a labeled node. And at one label per class, where we get very poor accuracy, it took on average over 10 trials, it took like over 200,000 steps before it hit a labeled node. There's only 70,000 nodes in the whole graph. And I stopped the random walker if it got to 1 million, which did happen several times. So it's actually much larger than this. I just wasn't patient enough to wait for this to finish. It gets better as you add more labels, but still, even at 4 labels per class, 14,000 steps is a lot, given that, there's only maybe 6,000 or 7,000 nodes in each cluster. Okay? Whereas when you get very good results at 160 labels per class, it takes only a handful of steps, like 50 steps, before the random walk stops. So what's happening is that your random walker is taking too long to hit a labeled node. Its distribution's mixing, and basically converging to the invariant distribution over the graph before it hits a labeled node. The invariant distribution on a symmetric graph is just the degrees of the graph. So if you let the random walker walk for a long time, the probability of finding it at any given node is just the degree of that node scaled by the sum of all degrees to make it a probability distribution. And so essentially what you can say is that the solution to Laplace learning in this very low label rate regime, it becomes a constant precisely because you're sort of averaging the labels against the invariant distribution of the random walk, which is independent of where you started X. And it tells you that, this should become a constant. And it also tells you what the constant is. It's the weighted average of the nodes, of the labels, weighted by the degrees of the labels. And so what happens is you're essentially, once you do this for classification, when you choose the label for the node X, you're just looking at the closest one hot vector to u of x. And if all of the u of x's are the same vector c, you're going to put everything into one class, right? And this is why you see this catastrophically bad performance, that like 16% is similar to guessing. Well, if you put everything in one class, you're basically getting 10% accuracy, right? So this is exactly what's going on at these very, very low label rate regimes. So to test this, we just did a simple shift in the label decision where we shift by this constant to get, essentially a function that has mean value 0 in all the coordinates. And this made a dramatic difference in the accuracy. So shifting by this constant went from 16% to 88% accuracy and so on. You get much, much better results with a very, very simple shifting technique. And so what this tells you is that, okay, the main problem at low label rates with Laplace learning is this large bias term that you have this constant vector that the solution concentrates around, and that constant vector is nowhere near where you're going to threshold to decide on class membership. And when you account for that by shifting the solution U, you get good results, which tells you that these spikes, in this case, these spikes are still present. The spikes are still there, but I've subtracted off this constant. And so the spikes do contain enough information, the tails of these spikes contain enough information to propagate labels. So, we could have, let's say, proposed to do this shifted Laplace learning and say this is our new algorithm to compensate for Laplace learning at low label rates, but it didn't really sit well with us because you're now doing harmonic extension of the wrong labels, right? The shifting of the solution U is the same as shifting the labels beforehand. And so it's like you're doing a harmonic extension of the wrong labels to get better results. There must be something sort of deeper going on here, we thought. And so what we came up with is the following heuristic argument, that if I take a solution to Laplace learning, which is roughly constant with these sharp spikes, it turns out I can compute the graph Laplacian at the labeled nodes as well as the unlabeled nodes where it should be 0. So at a labeled node, we just compute Laplacian of U with the definition here. You're at a labeled node, so U of x is G of x, the label vector. And if you really are in this situation where you have these spikes at the labeled nodes that drop down immediately to a constant at the neighbors, then all the neighboring values U of y are a constant vector C. And in this case, I can sum over y, I get the degree of x. And I get exactly a sort of an approximation, at least, for Laplacian of U at a labeled node. So now I know the Laplacian at labeled and unlabeled nodes. It's 0 at the unlabeled nodes. And so I essentially get that, this spiky function that we were looking at before, it approximately solves a Poisson equation on the graph, where I stick sort of point sources and sinks at the labeled nodes. And I solve a Poisson equation where I've dropped the hard constraints that I used to have at those labeled nodes. So the point is there's this connection that we didn't really realize until getting into this. There's this connection between setting hard label constraints in a Laplace equation and solving this kind of Poisson equation. There's a connection here in these very low label rate problems. And so we ended up dropping this degree because it gave us better results, and it kind of comes from the ill-posedness in the Laplacian. So we ended up proposing Poisson learning, which is the same kind of Poisson equation with the degree dropped. And this should replace Laplace learning when you have very, very few labels. A couple of words about the equation here. So because the kernel of the graph Laplacian is not trivial, it has constant functions in the kernel, there's a unique solution only up to a constant offset. And so there's an extra condition here that the weighted mean value of U is equal to 0, weighted by degree, which we can explain from a random walk argument that I'll show later. And then on the right-hand side, so a graph Laplacian always has mean value 0, right? So if you take the mean value left-hand side, you get 0. The right-hand side should have the same property for existence of a solution. This is like the compatibility condition for Laplace equations in the PDE context. And so the centering by the average label vector G bar, the role of this is to make sure the right-hand side has mean value 0. Okay, so then you get existence and uniqueness of a solution on a connected graph at least. So you solve the Poisson equation, you set the labels based on the maximum component of U, just like in the Laplace learning setting, but you can also account for unbalanced class sizes or unbalanced training data by reweighting the label decision. The way you do it is you reweight the components of the function U so that the sort of mass of the delta functions you're putting in each class is proportional to how many nodes are in that class overall. And this gives you better results when you have unbalanced data sets or unbalanced training sizes. So we went back and said, okay, because we had this random walk interpretation for Laplace learning, which led us towards Poisson learning, can we go back and find a random walk interpretation for Poisson learning, which is independent of that sort of ill-posed random walk that we were looking at for Laplace learning? And it turns out the sort of interpretation is dual to Laplace learning. What you do in this context is that you take a random walker for every labeled node, and you release them and see how they explore the graph. So this is these x0, 1, 2, superscript x is the node where I'm starting. And what you do is you sit on an unlabeled node x, and you just record every time you get visited by a random walker from one of the labels. You record its centered label vector, and you add these up over this process, over capital T steps, normalized by degree of x. And take the expectation. Okay, so you're just sort of counting how often you get visited by each of the labels random walkers. And the one that sort of visits you more often sort of wins out, let's say. So what you can prove is that as you send capital T to infinity, this function ut of x, the sequence of functions, converges to exactly the solution of that Poisson equation on the previous slide. And it selects the solution with the weighted mean value of u is equal to 0, weighted by these degrees. What's nice too is that it gives you an iteration, so you can write ut plus 1 in terms of ut. And it looks essentially like gradient descent, right? It's a heat equation on a graph where I have the source term from the delta functions and I have the graph Laplacian here. And actually, this is the first way that we solved the equation, was to just iterate this until convergence. Of course, there's a variational interpretation for this as well. So it's one of those sort of soft constrained problems I showed on one of the first slides, but it's a very specific loss function. It's a linear function of u, and it's just the inner product of u with the centered labels here. There's a minus because you're minimizing this, but really you want to maximize the alignment of these label vectors. And so the theorem is that if you minimize this over mean value or over 0 mean value functions, then there's a unique minimizer, and it's also the unique solution to the Poisson learning equation. There's an important point to make, is that you don't see a lambda showing up here. There's no weight in front of the loss function, which it's very common to add a penalty weight lambda here to sort of trade off how much emphasis you place on the loss versus the regularizer. So it turns out, because the loss is a linear function of u, adding a penalty here, lambda, would not change the classification in the end. It would change the solution by scaling it by lambda, essentially, or by like 1 over 1 plus lambda. There's some constant that the solution u gets scaled by. But when you threshold to get the label decision, you get the same classification regardless of what you place for a weight in front of this loss term. So you don't need to add an extra parameter. It's sort of a parameter-free model in that sense. And so all of this theory that I've been talking about is from our ICML paper from last summer. So if you want to read any of the proofs of this stuff, you can find them here. Let me say there's a continuum perspective. I don't want to say too much about this so I can get to the results, but we do want to be able to show that this Poisson learning is stable and well posed at arbitrarily low label rates. What we expect is that if I take sort of a discrete to continuum problem where I have an infinite amount of unlabeled data and just a fixed amount of finite labels, which is the set gamma, that the solution to Poisson learning should converge in the continuum to the solution of a continuous Poisson equation with delta functions at the labeled points. And so we aim to prove this kind of result in order to show that Poisson learning is indeed stable and informative at these very, very low label rates. And so this is sort of ongoing / future work. We think we can prove this with spectral convergence rates, because there are spectral representations for the solution of Poisson equations, and in other work we've proved very sharp sort of Lipschitz semi-norm convergence rates for the spectrum of graph Laplacians. But let me get to the numerical results. So you can reproduce all of these results I'm going to show you with our Python package for graph-based learning. You can get it on GitHub here, or actually now it's actually a Python package, so you can install it with pip, and it has Poisson learning plus 10 or 20, or there's like 10 other algorithms for semi-supervised learning. There's a few clustering algorithms. So if you're someone who uses Python a lot, please check this out and let me know if you have any feedback about the package. It's still fairly new. So just to write down the algorithm quickly, it's very, very simple to implement Poisson learning. It's a very simple iteration with just matrix vector multiplications. It runs quickly because you don't have to run it until convergence to like machine precision. You can stop a lot earlier. You can get good results. So we need about 100 or so iterations on these big data sets like MNIST, fashion MNIST, and so on, which takes 4 seconds. It depends on your laptop. If it's a slower laptop, I've seen 8 seconds or so. But you can put it on GPU very easily. And we have a GPU version which takes like 1 second to solve. And most of that time, if you sort of break it down, is just spent putting the data onto the GPU, it turns out. So we tested on MNIST, on fashion MNIST, and on CFAR10. So MNIST and fashion MNIST are kind of toy data sets. CFAR10 is a lot more challenging. So it has color images of various quality of in 10 different classes. So in each case, we built the graph by training autoencoders. So an autoencoder is like a nonlinear version of PCA. You have an encoder and you have a like low dimensional latent space, which is like a bottleneck to go through. And you have a decoder, and you train the autoencoder to compress and decompress your images with the sort of best reconstruction possible. And it learns a sort of good quality latent representation of your data, which usually has better geometric properties than your original data set in the pixel space would have. We used very, very simple things for MNIST and fashion MNIST. We used a 4-layer variational autoencoder with only 30 variables. So you're going from 784 variables down to 30 variables in your latent space. CFAR10 is much more challenging. We ended up using an autoencoding framework from a recent paper called autoencoding transformations. It's a little bit different idea here. Here you take the encoder has 2 inputs, so it has 2 images that go into it, and one image is your original image and one is a transformed image, where you apply a random transformation from a group that you select, like affine transformations. And the role of the decoder is that given these 2 encoded images, the role of the decoder is to decode the transformation that was used here. And when you train this to accurately decode the transformations in a group of transformations, you learn feature representation for your images, which is invariant to that group of transformations. And we used affine transformations in this case. It's actually not really dimension reduction. It ended up using 12,000 latent variables, which is about 10 times as many as the number of pixels in the CFAR10 images themselves. We compared against a lot of different methods for semi-supervised learning. In the first round that I'll show here, these are all methods that don't use prior knowledge about the size of the different classes. And in each of these cases, Poisson learning works a lot better than most of the other algorithms, although some are a bit competitive, like WNLL when you get to higher label rates, and P Laplacian. And this is run over 100 trials of randomizing the labeled points, and it's 1 to 5 labels per class, and you're seeing the standard deviation of the accuracy in brackets over those 100 trials. Fashion MNIST, the results are a bit worse because it's a harder data set. But the same trend is shown here. You can sort of compare these kind of results. When you're looking at semi-supervised classification with very few labels, it's more apt to compare it to clustering. So if you look at like what are the best kind of clustering results that people are seeing for these data sets, you can look at sort of a paper in 2019 by McConneville, who got 67% accuracy clustering fashion MNIST. So we can sort of exceed this with only a handful of labels per class. And the same for CFAR10. You get worse results, but the same trends persist. And again, the clustering results here are in the low 40s or so. Let me just briefly say that you can improve these results by adding volume constraints, which is to add prior knowledge of the size of each class into into the classification algorithm. And so we were inspired by this paper by Matt Jacobs, where they constructed this volume constrained MBO scheme for various applications, but one of them was for graph-based learning. And so when we're thinking about this Poisson equation, if you look at the iteration that we're using to solve the Poisson equation, if you replace the 1 over degree that we had before with a fixed time step over all of the nodes, what happens is this flow becomes volume preserving, actually, which is not the case in most of these applications. The reason it's volume preserving is that the source term with the delta functions has mean 0, and the Laplacian also has mean 0. So you're preserving the volume. If they're one-hot vectors, it means you're preserving the number of points in each class. Of course, they diffuse away from one-hot vectors. So if you alternate this with a volume-constrained label projection, which for this we just sort of adjust the weights with a very simple automatic algorithm to get the right number of points in each class when you project. You can think of this as sort of if you grow or shrink Sj, you're sort of growing or shrinking the region for class J, right? And so you adjust these weights a little bit to get the projection to have the right numbers of points in each class, and you iterate these two things back and forth only a handful of times, like 6 or 7 times. It's called PoissonMBO because it's based on the Merriman-Bentz-Osher scheme MBO for curvature motion, which goes back to 90s or something, which is a similar idea where you diffuse threshold, and you can generate geometric motions from this. And it was used for semi-supervised learning in papers going back to 2014, and then recently the Jacobs paper that I mentioned. So PoissonMBO works better most of the time, or all of the time. It can be quite a bit, like 6% here, or it can be sort of only marginal. And the idea is that, okay, you're doing better because you're using prior knowledge about the number of nodes in each class. You're getting the number of nodes in each class correct, whereas in Poisson learning, you might be having one class which is too large and one which is too small. And it's comparable, so it's better, but still, volume MBO is fairly comparable with this method. I mean, at the very low label rates, it's a bit worse. So, volume MBO also uses the prior knowledge about class sizes. The same kind of things hold for fashion MNIST, and here I'm showing higher label rates too, so 10 up to 160 labels. And same kind of thing for fashion MNIST, or for CFAR 10. Let me just say very, very briefly in the last few minutes of the talk that we've been looking at other applications of Poisson learning as well. And one thing we've come across is segmenting meshes. And so this is from a separate project, which is a collaboration with Peter Olver and Katrina Yezi-Woodley from anthropology at the UMN. And we have a consortium actually for the application of mathematics to anthropology. If you want to see more about this, the website is here. This project, which is NSF funded, has a couple of main threads, and one of them is the classification of bone fragments based on the agent of breakage, which has applications in anthropology. We're thinking of these as being fossils that are from dig sites that are 1 million years old, and you want to understand whether the fossil was broken by a human with stone tools, or by animal bites, or by natural causes, and so on. So one aspect is the automatic classification of these fragments, and the other is the automatic refitting of them. So it's a project that has lots of students involved, both at the REU level and graduate students. And one small aspect of it is the ability to segment a mesh. And so this is a broken bone fragment here. You want to segment it into the broken faces separated by break edges. And so for this, we ended up using some graph-based learning. So you can build a graph over the mesh by connecting nearby vertices on the mesh with a weight that depends on how similar their outward normals are. So if they're similar, it's a large weight. If they're not similar, if they're across an edge, they should have a small weight. And the result here you can see is actually just from spectral clustering. But we found that this didn't work very well in practice for lots of different fragments. And it's very hard to tune the results if they don't work well. So we ended up using Poisson learning, where you allow the user, like the anthropologist, to select a point in each face that they want to segment, and then you run Poisson learning, and it segments the mesh like that. So it's like it's a semi-supervised or co-supervised mesh segmentation. So here's 3 different examples, another more complicated example here, another one here. So these are screenshots from our MeshLab plugin. MeshLab is this mesh optimization package. You can write plugins for this, and we have a plugin for the mesh segmentation and for other things that we've been working on. And you can find this stuff if you like at the software tab on our web page. So just a couple of words about future work. We're looking at future directions for Poisson learning, like directed graphs and a version of clustering based on Poisson learning. We want to understand this continuum limit that I mentioned earlier, and then also to go beyond that to understand the asymptotic consistency. If I have sort of approximately clustered data, is it going to uncover the correct clusters, and what kind of label rate do I need to ensure that? And then, there are natural extensions of these kind of arguments for controlling the spikes to the P-Laplacian regularizers. If you use the so-called game theoretic P-Laplacian, there's a two-player stochastic tug-of-war game interpretation, which is the analog of a random walk interpretation for the two Laplacian, and the same kinds of ideas work in this setting. And so this is current work that we're looking at, and I think some of these ideas would hold for other kinds of graph models like stochastic block models. And then, we want to understand some stuff about the connections between Poisson learning and some recent work in graph convolutional neural networks. And there's this new sort of problem in machine learning called few-shot learning, which I think these ideas would be useful for. And it turns out, we just noticed this fairly recently, that another group has picked up our Poisson learning framework and has applied it to semi-supervised few-shot learning in a conference paper that's going to appear this year. And so this is a direction that we'd like to also pursue in the near future. So thanks a lot for listening. These are the two papers I talked about, and this is the Python package I mentioned as well. I'm happy to discuss and to answer questions.